What I go back to it, but I just want to remind you of is we call it theorem 1. And since last time I didn't put the authors, maybe I'm going to put it now. Rabsky, Pan, myself, and Wilson. The first two authors did the numerical part, which I didn't really talk about it, but definitely they were fundamental in that. And Bobby and I did more the analytical part. And it says, suppose we are a torus of dimension 2, and it's, let me say this is, let me make explicit period T1 and period T2, and T1 over T2, and what I call omega is algebraic. Oops. An algebraic number. Okay, now let the NLS star, if you remember, that was a little bit of the notation. With this, I mean DTU plus Laplacian of U. And then here we have not the full nonlinearity, but only the quasi-resonant. Now, don't worry about the quasi, just think about the resonant. And last time I explained how in this particular case, when the irrational case, the four-wave resonance set split into two one-dimensional resonance set. And then I showed you how for the 1D resonant NLS, all the DS norm are basically conserved. And so using that kind of splitting, you will prove that the DS norm of this guy are also, for the quasi, for the resonant, is also conserved. Then the quasi connected with this algebraic property of your torus tells you that basically, even if you are quasi-resonant, close to being resonant, the frequencies that are only quasi are finitely many, and they are inside a ball, so they're basically, you can ignore them. But for now, just to remember from last time, just think about resonant. So there is an initial data, and this is in HS, S greater equal than 0. So the equality is the thing that is really new in the sense for S equals 0. Without this restriction, even local well-posedness, it's open. It's a critical exponent, but in here you can do it because, again, this property of irrationality. So then, NLS is globally well-posed, and moreover, you have a bound for the HS norm. So, and for any solution, you here, well, the important thing it's greater than 1 because otherwise we knew constant. Okay. Now, there is the opposite of this, in a sense, in the following theorem 2.
It's bounded in terms of initial data.
Absolutely. It's, this C will depend, just to be, this will depend on S itself, will depend on the norm of the initial data, and the alpha, omega, whatever, all of this. Okay, so theorem 2. This is by the I team. So Colliander, Keel, Tao, Takaoka, myself, and says the following. Now we assume that the torus, still torus of dimension 2, but let's say for simplicity square torus, but this is, I'm going to tell you in a second, you have a generalization of that. So in this square torus, and then we fix S greater than 1, that's the order derivative, a sigma, which is greater than, greater than 0, but very small, and k very big. Then there exists an initial data in edge S with the norm smaller than this sigma, and there exists a time which is very, very large, such that the solution to NLS, now the full NLS, not the star one, cubic eddy focusing, U is such that U at this large T is greater than K. Okay. We prove this today, at least give some kind of idea of the proof. Theorem 3. I'm going to, yes, no, Sergio.
Well, that's quasi-resonant.
Yes, because so quasi-resonant, for the class, think about resonant, that's fine, but quasi-resonant is just a little bit fattening the manifold of the resonancy, just a little bit larger than that. So the precise definition is that, let's say lambda 1, lambda 2, lambda 3 are the symbols of your Laplacian in this torus. Then lambda 1 minus lambda 2 plus lambda 3 minus lambda 4. So this is greater or equal than 0. The 0 will be the resonance. And lesser or equal than some constant that you can pick. And then now here you have the sum I1 to 4 of ki to the 1 plus tau. And you can pick which tau, which lambda there are. And of course, also you have that k1 minus k2 plus k3 minus k4. This is 0. So that's the quasi-resonant side. But don't worry about it. I mean, I was saying before that the strictly greater than 0 and less or equal than this are actually finitely many. And so you can just ignore them, really. At the end of the day. So really the resonance are what's important. Okay, theorem 3. This is by Giuliani and Guardia. And this is super cool because here you use, for this theorem, you really use that you are in the square torus. And you have this growth. And it turns out that the proof of this, it's all, and as I will show you today, it consists in looking at the resonant NLS and saying that that grows, which is exactly the opposite of what I'm telling you there. So really you cannot do this construction in a torus which is not square or rational would be okay. But there is a perturbation that you can do to this proof, perturbation of the manifold here, of the torus. It says the following, that if, well, I'm going to abbreviate a little bit. So it's a better state, I mean, it's a more precise statement in their paper, but just for today. So if T2 is irrational, and omega is the ratio, okay, up there. So which is T1 or T2, is well approximated by rational. It's very precise what it means, well approximated by rational, but your intuition, it's enough for this. Then this theorem, theorem 2, holds. But I can tell you that the proof, this proof, will not hold here. It's really perturbation of the manifold somehow. You have to approximate this torus with tori that have a rational, the rational ratio here, and then use this, and then take a limit in the right way. So that's how the proof goes.
What was this called? The theorem?
Oh, this was before pandemic, so, but not much before pandemic. So, okay. I know, this is, now that's how we, okay, theorem 4, like I said, I'm going to state a bunch of theorems, then I only prove the 2 here. But just to see them all together, it's important. Okay, so theorem 4, this is by Hani, Posadeur, sorry. Tsetkov and Vishilia. And I mentioned briefly last time, but I want to state it now. Okay, so consider NLS, and by the way, I mentioned it, I didn't write it, but for me NLS is always cubic NLS defocusing, okay? So consider NLS in now R cross TD, and D is greater or equal than 2. And TD is rational. Okay, so then, there exists S0 and epsilon 0 greater than 0. So this is large, this is small, such that if S is greater than S0, so it's 1 is probably not enough, but just it's a large order of derivative, which is what we are looking at anyway. And epsilon is less than this epsilon 0. So then, so there is these two guys that if S and this, then there exists a U0 in HS, U0 less than epsilon in this norm, such that the solution starting from U0, let me give it a name. From U0 has the limit as t goes to infinity of ut in HS to be infinity. So this is actually the only case that we know that there is a growth to the HS norm. But it's a little bit more precise than this. In fact, there exists a sequence of times tk goes to plus infinity, such that the norm of u at tk in HS is bigger or equal than a constant exponential of log tk 1/2. That's it. Okay. All right. So that's the result, and it's the reason why I put them in this list is because to prove that you use where did it go? This construction, and I will show it to you how you use that construction. And now you might say, okay, if you're using this theorem, then you might just as well use also this theorem to prove that theorem when TD is irrational but well approximated. That seems obvious. We are trying to prove that. There are, it's a delicate thing. I believe it's true. We are halfway into the proof, so but I cannot state it because it's not finalized. It's more subtle than what you believe it's true, but it's subtle. Now, the opposite direction is also true in the sense that if you are irrational, well, you can say something. And this is the last theorem I'm going to state. Theorem 5. This is Camp and myself. By the way, Nicola Camp is coming to give a seminar, I think it's April 14. So I'm not sure what he will talk about, but now consider, this is stated in a little bit different way. So the cubic defocusing, I'm going to call it NLS A, you will see why, on R cross TD. And this NLS A is the following system. So I dtu, then there is second derivative in the x coordinate, which is here. And then there is slightly different way of thinking about divergence of A grad y. The y, so here is the x, the y is there, of u. And this TD is square. Okay, now this is it's written in a slightly different way. So the torus is square, but then you dilate it or whatever with this matrix A, which I'll tell you in a second what it is. U0. Okay, so what's A? So A is the following matrix, where A is matrix constant coefficient such that the transpose of the vector A times capital A, then B. This is in the little L2 norm. It's a finite dimensional thing, so it's a little bit exaggerated to say L2, but anyway. This is less or equal than, greater or equal than, sorry. C, A, L2 tau, B, L2 tau, for A and B are in ZD minus 0 square. So these are just elements on the lattice ZD. They are not 0. And when you compose it that way, that's for some C.
How much is that?
Any bigger than 0. So for some C and tau. Now, if tau you take a large enough, the set of this kind of matrix is a full measure. So there are a lot of them. Tau greater than 0. Okay.
Wait, but I'm confused. So A is a matrix, so it's multi. Oh, Dij. Okay.
Yeah.
So it's a secondary.
Yeah. Here. So this is like you can rewrite. So if A were diagonal, and in fact, if it were the identity matrix, would be just periodic in a square torus. But then if this condition is telling you that this is some kind of irrational way of writing it, or an irrational torus will give you. Okay, so it's a little bit more general, where A is like this, and then what happens? So if I consider this thing, then there exists an S0 and again an epsilon 0, greater than 0, such that for all U0 in HS and U0 less or equal than epsilon or less than 0. So okay, HS S greater than S0 and this epsilon less than epsilon 0. So this tells you for all initial data that are in HS and this is small, the following happens. Okay, now I'm going to have to erase this. Well, there is no growth. That's really the conclusion. If U is solution starting at U0, we have again, ut in HS, and this is R cross TD. So let's go on a constant. And again, the constant depends on all the things. So it doesn't not grow at all, which is the opposite of what happens there. Okay, so these are the theorems that I wanted to mention. And I raised one, but as I anticipated, this theorem here of growth is connected to this one, and I will tell you how in a second. And this theorem of no growth is connected with the theorem that I raised, which was
here
given
you
you.
have the full non-linearity.
Full. Yes, exactly. And the reason is because I'm crossing with this guy, and I have and I mentioned also, as I prove this theorem here, I have better control of the full dynamics of the system because I have dispersion in one direction. So they have decay 1 over T². That tells me that I can transfer what I learn about the quasi-resonant or the resonant to this condition, situation.
This is strange.
The first theorem, the one that you raised, there was no
Yeah.
Diophantine condition.
Yes, there was. That was,
Okay, so there
was
was-
algebraic, and
So-
here is this.
Yeah. So and they're not really, like here there is no quantitative requirement. In other
Quantitative.
words, tau is not controlled.
That's right. You can you can
Tau
ask.
be anything. And
Yes.
there also.
In there, so they are not. So that theorem is sort of a subset of this. This is a little bit more general of that, but we don't know yet. So there is not a condition on the irrationality of the torus that will tell you if you have it, then everything doesn't grow, and if you don't have it, everything grows. It's not. It's still not closed as a condition. Okay.
The distances are subtle. The distances are subtle because you have one copy of R. If you were to have two copies of R, then presumably.
Correct. Very good, Alex. Thank you for the question. As Alex said, if you have 2 copies of R, you have a lot of decay and you have no growth whatsoever. So
Then it becomes
that
Euclidean
thing,
theorem.
that thing, yeah, exactly, becomes Euclidean. You don't have any growth. There's scattering, all of that. So, and this theorem here becomes trivial at that point.
Because you get T⁻⁻⁻⁻⁻⁻, but that's still kind of borderline.
But it's enough.
Q squared,
It's enough.
so it's cubic.
Yeah.
Straight.
So it's.
But that's kind of a funny condition. So why?
They call it
You say if it was-
Liouville torus, and it's just a little bit more general than having
Okay.
a purely irrational and all of that. It's just a bit more general. Okay, now I'm really excited to show you the proof of this.
But
This,
you
yeah,
still require the matrix to be elliptic and everything. I mean.
correct,
Yeah,
absolutely.
yeah, yeah.
Yes.
So this is
Sorry,
only the lower bound that it's bizarre.
exactly,
Right.
exactly, and it
So
kind
in
of
particular examples, if you have off-diagonal terms that
Yes.
are, so I would have liked to see an example.
I will bring it next time. Yeah. So that's. But the point is that this kind of condition with the tau here and so on, that's the typical that tells you that you are not you cannot approximate well an irrational number. That's typical of that kind of. That's why you have that inequality. So now this theorem,
KM,
yes,
right? I mean,
So-
these are classical KM
Yeah.
conditions.
Yes.
Then there is a quantitative requirement, so they are full measure.
yeah, exactly. For that you need tau larger, not just greater than 0. Yes, Alex.
In these things, does it really matter that the operator is elliptic?
That's a very good question because we have also results for sort of.
Can it help you that it's elliptic? Because,
Well, Davy-Stewartson, for instance.
Yeah.
All this should work for Davy-Stewartson.
So then it
Yes.
Not elliptic.
Not
no.
elliptic. Yeah.
That's my point. Does it?
Yeah, and non-local, that's a different story. In other words, in software, you have another operator that gives you the U cube, it's not local.
if you plan on using Strichartz estimates, you don't distinguish very well before.
Absolutely, but
Right.
here it's a more than like when you saw last time I was proving this DS being conserved,
Yeah, okay, so it's maybe-
that is split in one dimension. So you have to. It's more delicate than that. Yeah, but it's not just
Don't use
Strichartz.
Strichartz.
To have an upper bound, polynomial upper bound, I agree with you. Most likely you don't see the difference because it's really Strichartz. But for this more refined thing, I think the manifold really makes a difference. Okay, so this theorem, it's, I'm gonna, so this is proved, I want to say just a couple of words. In original proof, there was not a very good estimate of how long this time is supposed to be. But then, and the proof, although has a flavor definitely of a dynamical system, it wasn't not done using the powerful tools from dynamical system. It was really done by hand, the estimates were done by hand and so on. But later on, Guardi and Kaloshin went back to this theorem, and there is now much better estimate of this T, what T is, and it was, this theorem was taken again when that was proved, and also in that case was better estimates for that. But I'm going to give you the first version of this, so just to give you an idea. So sorry I have to cover, but we know all the ingredients that we have to use. So it is a constructive proof, meaning you have to exhibit for me an initial data that has this. So because it's constructive, you can make assumptions, right? So I'm not proving for any initial data. I'm just trying to look for one. So the proof of the theorem will be sort of a reduction of my original system NLS into something that I can handle better. And then, of course, you have to go back, right? From what you get at the end, you want to go back to the full system. And that will give you the restriction of not knowing what happens after capital T, not having directly this growth, and all of that. But I will make a note of that as we move along. So proof of theorem 2. Now, I'm going to put quotation mark because not all details will be given here at all, but it's sort of a blueprint of what is going on. So I'm going to divide the proof into ingredients. The first ingredient. So the first ingredient, it's really try to reduce or move from NLS, the full NLS, into a toy model. And I have to say, although it wasn't the original proof, in the toy model, you actually have that kind of logarithmic growth. We didn't prove it there, it was proved in that paper, but the toy model does have the logarithmic growth. And so, say it again?
The log.
The log. Actually, it's log. It's,
Take
yeah.
a log of both sides.
Whatever, yes. Anyway, so some log of some power, whatever, I think. The problem is, how do you go back here? So this is where you lose things. Right. So this is where you lose things. And in original proof, we couldn't really go back for the full extent of the sequence TK. And we, with our lemma, stability lemma, we could only go back to a certain time, t. And then in that proof, the fact that you, as I mentioned, you have dispersion at least in one direction, that was the reason why you could actually move back from the toy model to the NLS. Okay, so that's so the first step is going from NLS to the toy model. And how do we think about that? You expect, or you make the assumption that this growth should come from the resonance. That's the original idea. And so I'm going to go back to each of these ingredients, but let me just briefly say what it is. So go from, one thing to remember is that if you start with the NLS, with U, then you take Fourier transform of that, and you go to infinite system, infinite Hamiltonian system. For AN, which is the Fourier transform, right here. ANT, which is the Fourier transform. So I'm going to move from the x variable to the n variable via Fourier. And this is an infinite Hamiltonian system. And not just that, it would be OK if you had only nearest neighborhood interaction, but you have interaction everywhere. So it's really hard to take care of it. So we're going to take resonant quadruplets. I will go in detail, but and define a special set lambda among the resonant set. So it's a lambda is going to be a subset of the quadruplets that are in resonance. Okay, I set lambda inside of 4 waves resonance set. Now, this set lambda, I'm going to tell you from the beginning how it looks like. It looks like this. So you first excite at 4 frequencies. By the way, it looks close in my blackboard, but they're actually going to be farther away. So you excite this guy, and then this one. And then you keep going with this. Sorry, where am I then? Yes. And then we keep expanding now in that way. So this is going to be between squares and diamonds, and then square and diamonds, and so on and so forth. So this is basically how it looks like, this set lambda. And we're going to define via generation. So this guy, for example, are going to be parents. The square are going to be children. Then this is going to be the next generation, and so on and so forth. I will describe this in details, but I just want to give you a picture of where it's going to, how it's going to look like. And my dynamics will work in here. It will be purely there. Now, the second ingredient, so we're going to get from here a toy model that lives in lambda. So ingredient 2. So in this second part, we're going to look at the dynamics of this system. And because the conservation law, in particular conservation of mass, the whole dynamics is going to live in a complex sphere. In other words, this is just the size of the absolute value of the vectors that come from the dynamics are going to be, let's say, size 1. That's the conservation of mass. And then you discovered in the dynamics of the toy model that there are, I don't have colors, there are big circles that I'm going to call a tori, sorry for using the same word. So there is a T1, there is a T2, and so on. So there are these tori that are invariant, meaning if you happen to start with an initial data here, it just keeps rotating. And then you realize that really what you wanted to prove, which is this forward cascade that we're talking about, is to go from torus 1, there are many of them, up to, let's say, torus n. You have this parameter n. And this first torus is going to indicate low frequency, and this one is going to indicate high frequency. And what you want to do is, of course, you don't want to start here, because then you don't go anywhere. But you want to prove that you can start nearby, avoid all the other tori that are here, and end up here. OK, that's kind of Hartnett diffusion type of thing. And that's what we prove.
Diffusion by hand.
By hand, exactly. So this is where we reduce. So this is what we can say about our torus. Now, I wanted to anticipate that we stop here in the proof. We take this and we transfer back to the LS via some kind of stability lemma. But what was gone in that theorem is this set, which is attached to a certain parameter n, basically tells you that this construction happens within how do you call it? In between 2 spheres. So it doesn't look like in the picture, but that delta set is in this region. And this is, let's say, R, and this is NR. But R is fixed, and N is a parameter. And everything lives there. Now, what they did was changing this parameter N, meaning you define this, let's call this set lambda n, which lives here. But then as you, let's call this n1, you can repeat this construction for another n2. But the problem is, you have to make sure that these annuli are really far from each other. Otherwise, they start interfering, and you cannot really pull everything together. That's what they do there. And the n1 will give you the t1. And then as you move up, you get a tk. And that's where the growth comes in. Okay, just to give you an idea. But
So this is for the second.
that's for the second, for there. This is just the general idea how they got that one for the toy model. But we stopped at this level with this parameter. And I will give you this construction. But then in a sense, if you concatenate this type of behavior that happens in these annuli, which are far from each other, hence there is no interference between them, you can take something that grows and grows. That's the idea of this construction. So let me go. Now this is the ingredient 2. I think this is the most important one, because this is where you study the dynamics of the toy model, and the one that we did by hand and the other people did with more sophisticated tools.
Before you ask the last
Yes.
question, so in theorem 4, of course, it doesn't matter the dimension, but in theorem 5, do you need the restriction of dimension being not too big?
No, actually we can prove this for everything.
But how do you do it even on R to the D? Becomes super
R to the D? No, here, no.
How do you prove global regularity even for R to
This small data, and you are very high in regularity. Yeah, this is small data. This is in comparison to that, right? Which you start the small data, you have a growth. This is small data result. Yeah. Yeah, you have to see it in comparison to that one. Yeah. It's right here. Okay, so let me go to ingredient 3. But that's the bulk of the theorem, really. Okay. So this is the part in which now you wanted to go back, and it's the approximation lemma. Okay, so here we take ingredient 2 and push back to NLS, and this is the limitation. Of the theorem. In terms of not knowing really what happens after capital T. And then ingredient 4, this is basically nothing really. So when you do this part, you don't care yet that the initial data has to be small. But if you wanted to have the claim this theorem for a small initial data, just do rescaling. To make sure the U0, so the initial data in HS is less than epsilon. But this is okay because since S is greater than 1, HS is subcritical. So rescaling is possible. Makes U0 small. Okay, so that's really nothing, just to conclude so that you can make the initial data small. Okay, so let's start with all of these ingredients. So the toy model. So I'm going to start, well, we say that the torus is just the square torus, 0 to pi, so that makes things easy. So I'm going to do a little gauge transformation, but for to make things a little bit, look a little bit nicer in the Fourier world. So this is, so let's say M be mass. And I'm going to define V to be my original U, but e to the I think plus, yes, 2 times t. Where U, so this is my definition, so U solves the original NLS. Okay, so then I would like to write V, so we write V again as the following. Vxt, this is a and t, and then e to the I and x. This would be if it were just Fourier transform. We took Fourier transform. This is just the Fourier coefficient. But I'm writing it with respect to this modulation, if you like. In other words, if this were constant, this will be just initial data, right? Sorry, this will be the, okay, so when t is 0, this will give me the initial data. But when t is constant here, this will be just the linear solution of the problem. The fact that there is a t here will incorporate in here all the nonlinearity of the problem itself. And if you make this transformation, then what kind of equation does the AN satisfy?
So how does M show up?
I'll show you. Let me write the equation, and then I will see. So this guy satisfies the following equation. IA dot n equals minus 2m AN. And you say, why are you making your life complicated by adding this piece? And I'll tell you in a second. Plus sum n equals n1 minus n2 plus n3. This is the convolution. And then an1, an2 bar, an3. And then here you have e to the I omega 4t, where omega 4 is my resonance relationship. Plus n3, my n4. OK, so why did I put this thing here? You will see in the next step, because let me define now.
So yeah, about n4. So there is n1, n2, n3.
N, sorry. This is n.
Okay.
Thank you. Yeah, this n here. OK, now let me define the following gamma of n. This is my set n1, n2, n3, such that n1 minus n2 plus n3 is n, and such that n1 square minus n2 square, oh, I have already the definition of omega 4. So omega 4 equals 0. But I also want that n1 and n3 are not equal n2. This is my set omega. And I'm going to restrict. The first restriction I'm going to make is to assume that this n1, n2, and n3 live here. And if I do that, I get the following.
The identity, the sum is taken.
Probably, some sign.
Gamma n, because you already put the 2MAN outside.
That's right. So I didn't, for now, I didn't restrict anything. In a sense, this is my original system.
But once you put the 2MAN
Exactly.
outside,
Then that will be canceling. Then this will cancel this thing.
But so what do you make the assumption? The n1 and n3
Right. So that let me. So let's
okay.
define this
It's
first.
just a resonance set, right? So you.
I'm going to define
It's
this.
a subset of the resonance set.
Those are the worst reasons.
Yes, they are exactly. They are the worst resonance, exactly like that. So let me. This for now. Okay. Do we agree? I want to make sure that it's clear that At the moment, this is basically the same as NLS, except for this little gauge transformation, which is trivial. So I didn't do anything. But now I start.
It's a resonant analysis, right? So one.
No, now this is just the whole thing. This is the whole system. This I didn't say, but this Ni are in Z2. This is the whole system.
Once you take the 2m outside, don't you have to restrict the sum to just n1 and 2 in gamma n? Because you already have the m outside.
That actually might be correct here, but that's still equivalent. Let's write, Alex. And then 3, no equal and 2. Do you agree now? Okay, good. Perfect. All right. Sorry, I might have made things in a way that maybe this was the A. Okay, let me just modulo something.
I don't understand what
Alex is saying that this thing is accounting for when n1 and is equal to n2.
Why n1 is equal to
Why does it?
And then,
Why the norm? Because the norm, you should put them together.
okay, so let's think for a second.
If n1 is equal to n2, you get this, the a and the m, the n.
That's the mass. That's the sum of n squared, which is the mass, which is this. And then, so if n1 is equal to n2, this cancels, then n is equal to n3, and that will count for that one. Good, all right. Anyway, this is not the hard part. It's and if I might have made some mistake of signs and stuff, but okay. And I think for you ask why do we do this? So why do we do this gauge transformation here? I believe. And why do we do this? Actually, this is more important. So if we do this, we don't see the Laplacian here.
Okay.
That's, yeah. Otherwise, you will see the answer. Okay.
And we put the Z2
So.
there for my satisfaction.
In here,
The
here.
definition, no, the definition, the first line, the definition of.
Ah, thank you. Thank you. Excellent. You're right. That's where you came the first. No, this is
I
too
thought
deep.
that you're using
Thank you so. Yeah.
This is the one.
No, this is. Okay, so then, so at the end, now I'm going to make the first, this is equivalent to the original system, just written in the Fourier world. And then I'm going to assume, well, consider. So now I'm going to call it NLS R for restriction. And this is going to be, and now here, n equals minus 2man, and then the sum, and now my frequencies are, so I want to say that n1, n2, and n3 are in this set here, gamma. And so what you see, and that's it. The omega now is 0. Because I'm doing the resonant part. Okay? Now I'm going to rest. This is no longer the original one.
Okay.
I made a restriction. So you see, we already lost something, right?
Yes.
Because of, okay. Okay. Now, I'm going to make a further restriction in the sense, in this big set, by the way, this, when you take the quadruplets n and 1 and 2 and 3, they are vertices of rectangle or diamonds. In that big, huge set of resonancy, I'm going to pick a special set lambda, which I gave you already an idea before, but now I want to give you.
So it's still an infinite-dimensional.
Yeah, of course. Yeah, that's, yeah. But slowly we're going to go to the finite dimension. In fact, the point now is to define a subspace here in which I will restrict my, my dynamics. And the set is the following. So we can, and this, I'm not going to prove this, but we can define a set lambda n with a parameter large, such that the following happens. Okay. 1. So lambda n, well, let me don't put this all the time now because it's going to be made by families or nuclear family, how we call. Lambda 1 union lambda 2 union lambda n. Now this is a bad notation.
It's okay, we live with it.
Okay, let me just look like that. It's a lambda n. And so these are made of nuclear families. So lambda i's are nuclear families of n1, n2, n3, n4. Now the last n I'm going to give a name, I'm going to call n4. They have the following property. So the n1 and n3 are children. And these guys are, I should say, sorry, the lambda are made of nuclear family. And these are, no, these are parents, sorry. I want to make sure that it's the same notation in the paper in case you go read it. Okay. Parents. And this one, 2 and 4 are children. And n1 and 3, they are lambda j. And n2 and 4 are in the next generation, so lambda j plus 1. Okay? Okay. But there are a bunch of properties more that we can talk about. So if I'm giving you a frequency n1, that is in some
At the end, you're ignoring
the boundary, what happens when you are at the end. Yes, you ignore. In fact, at the end, we'll
kill the children.
no, it doesn't have any more children. That last one. We don't kill them. So, yes. Okay. So we want some kind of uniqueness, and this is the second property. So for any j 1 to n, and for any n1, let's say in lambda j, there is a unique family. n1, n2, n3, n4. And similarly for the children. So for any, okay, the whole thing, and for any, let's say n2, there exists a unique family. So of course this n1 and 3 is going to be in lambda j, and the children, and 2 and 4, are in lambda j plus 1.
So given n1, you construct the others, right?
It's at the construction.
J by J.
J,
by J.
yeah.
So it's not for every J there is, and then 1 there is a unique.
Right. So
Given n1, you find
pick an n1. Okay, for any j, if you pick an n1 in this, there will be a unique family that contain that as a parent.
So this lambda, okay, so first of all, you didn't say the lambda j's are disjoint, right?
Yes,
Right.
they are disjoint. Exactly. Okay. Family and here, the n2
so
and
this
4.
comes all from adding and subtracting frequencies, right? Because it's the difference in nonlinear. It's a nonlinear.
You're organizing the resonance set.
Yeah, you are picking, there are all this. So imagine the resonance sets, it's all rectangles or diamonds, but all over the place. And here I'm picking something that will give me a nearest neighborhood interaction. Basically, that's where I want to go with this. So you don't want to, you don't want it to, this family, you don't want it to be too far, interacting with very far away. Because then when I'm going to write my system, what I want to achieve is the nearest neighbors that I can control better. So that's why you want to restrict everything on this. And of course, n1 and 3 is in the previous generation, so j minus 1. Okay. Then the fourth one, the fourth.
But I think it's unique. There exists a unique family.
Yes. So pick a frequency in this set. Maybe there is a way to.
Unique family having these properties?
No, I'm not saying that this is the only set that you can construct in this way. All I'm saying, what I put in this set is such that when you pick a frequency, that's going to be in one of the lambdas. And it's going to be it's a vertex of a rectangle such that the other vertices are organized in the way that you have, for example, n. So you have this. And you have, I don't know, this is, let's say, N2, and this is N4, and this is N1 and N2, and N3, sorry. So these are in the generation before, and these are together in the set that comes after.
Yeah, I know, but it's not unique. It's just...
No, it's not unique. You can
procedure.
construct, yeah. No, I'm not saying that it's the only way.
It's a unique procedure
Yeah.
if you want.
Okay. So this is important. So lambda, the whole thing contains only this family, this nuclear family. And nothing else.
In other words, now you make a big restriction.
Oh yeah, huge restriction, in fact. And then the last one, which is kind of, well, it's good when you estimate your Sobolev norms. If you take n in the last generation, lambda n, and you sum this is greater or equal than k squared over sigma squared of the sum of the generation at the beginning. So why is this important? So if you believe that kind of forward cascade that I indicated with the tori that are invariant, when you start from the beginning and you end to the end, then you start from here, you end up here, then this is the HS norm bigger than, that's just to make sure that you get the connection with the kappa and the sigma that you want. Okay. Now, what can we deduce from this? A bunch of things. Most important is the following.
So lambda 1 you associate it with the initial data, I guess, right?
Correct. The lambda 1 is exactly where you start, as soon as it's going to come. And the lambda n, where I'm going to end at the end of my... OK, so now finally we got to the toy model. I'm going to call it Tm. Actually, Tm tilde first, because I have to do one more iteration. And this looks like that. So I, A dot n, equals, let me ignore the part that was the 2 min, that's the linear thing. Let's just don't worry too much about it. So it's the sum gamma n, and let me write it like this. It's a little bit abuse of notation, but what I mean is that n, this guy, and n1, n2, and 3 are in this set, okay? n1, n2, and 3. And then my a and 0 is my whatever, the initial data that I didn't define yet, but that's where it's going to be. Now, there is an important lemma, actually, that says the following. So in each of these lambda, there are a bunch of frequencies. It's not just one. It's a bunch of them. But if I set at time 0 that the Fourier coefficients are exactly the same for all the frequency in each of these lambda j, you would like this to be a property that propagates. And in fact, it's true. OK, so this is what it says. So the lemma says that assume now this is going to be a hard thing to write, that A0n is equal A0m, let me write it like this, I, for n and m in generation lambda I. So I'm saying that I take different frequencies in the lambda I, but I set the initial data to be the same. And let's call it this B0I. Doesn't change. Then, and this is true for all I. So I'm saying that all the frequencies that are in generation I, I'm assuming at time 0 have the same Fourier coefficient. Okay. Then II and T is equal AI MT for all T. And I and N and so on. And let's call this B and T. BI, that's it. Is that clear? I want to make sure that it is clear. So in all the lambdas, so let's say this is lambda I have a bunch of N and M's, and that setting that my initial data is going to be constant here. And this is propagated. Okay, so the proof is not too hard. Really, the proof, you do the following. Look at ddt of AIMT minus AINT, and then use the system. And it is important that here you use, and the fact, the constructor really. Of the big set lambda, where there is the generation connection between that. Okay, so I'm not going to spend much time on that, but that's an important thing, because now if I'm assuming that my initial data are picked that way, because I'm constructing initial data, so I'm picking that way, then my toy model, which is an infinite dimension thing, becomes finite dimensional with this initial data. So this, using the lemma, the toy model now this is really the toy model, reduces to the following. With these B's, now I'm going to call it B because I'm assuming that at time 0 they're all, time 0 I'm setting all the coefficient in the same lambda I to have the same value. So I get the following system. Minus Bj square, and I apologize if there is some sign missing or whatever, but more or less T Bj bar plus 2 times Bj plus 1 square T Bj bar T. So that's my system now. Only interacts the nearest neighborhood.
And it was finite dimensional before too, right?
Because you could be inside the lambda, you can have a very large number of it.
Right. No, it's nearest neighbor. It wasn't nearest neighbor.
It was nearest neighbor, exactly. Okay, so, and now we have to, let me put the conditions at time 0. So Bj 0 is my given Bj, which I didn't pick yet, but it's some given number. And then there is the boundary conditions that come from the fact that we don't spill over. So B, let's see, 0t, this is the, or maybe 1, that's the first j, is equal B, the lower one, this is the upper one. 0. Put it like that. Okay, so this is much more manageable to deal with, but it's very far from what we started with. We made too many reductions.
Like a shell model.
Exactly.
Shell model of NLS.
But not the whole thing. Yes, exactly.
Not only that, but with all the what you call the profile NLS, because you removed the Laplace.
Yeah, we removed that. We made a lot of restrictions. Okay, so but we restricted a lot, but not completely, in the sense that it holds the following proposition. Mass, energy, and momentum are preserved, are conserved. So let me just use one of them. What's important for us? Let me say that the mass is, in this context, what you can guess is this. Okay? So that's our mass. And the ddt of this is equal to 0. Now we normalize, so this is equal to m at 0, and assume that m is 1 for us now. Okay? So we don't. So this is what I meant when I said that the whole dynamics lives on a sphere, a complex sphere of radius 1. So let me be a little bit more precise on that. By the way, these b's are complex vectors. So just to notation. The B1 or B0 or whatever, let's call it B1 because it's 0 anyway, Bn, this is a vector that belongs to Cn. Okay, it's complex. And then if W T equals the flow map, for the tori model. Now with this notation we know that if sigma by definition is let me call it it's the following sphere. So this is let's say x1 xn in Cn such that the sum of xi square is 1. Then, using the conservation of the mass and all my notation, this Wt takes sigma into itself. So everything lives on this sphere. So this is my sigma. Okay. Now there are I mentioned at the very beginning this tori. So let me tell you what they are. So if I'm assuming that Ti, let me call it Ti, to be 0, 0 all the way to the Bi, and then 0, 0. So all 0 except Bi, but Bi as magnitude 1. That's a complex number at magnitude 1. Then you can prove fact that Wt of Ti, yeah.
You just rotate on these guys.
Yes, exactly. Keep being on there. On Ti. So you're stuck there. And this is the obstruction to the forward cascade, really, for this system. That you will like.
The faster you are, the faster you rotate, so you have.
Yeah. Yeah. So yeah. So now this is pretty clear what you have to do here at this point. That's not now. So this is an obstruction because exactly what you would like. So you see, low frequency for me is when there is a B here, which is a size 1, and I would like to go to the one that's at the very end. That's the high frequency. But in the middle, there are all these things that are gonna.
The energy doesn't give you another obstruction.
The energy, when you actually do the, I cannot tell you that. Might give you definitely some other constraints, and probably we had to work harder. But now I cannot think of something explicitly to write about that. Okay, so let me just now. I'm wondering if you. Okay, the proof of this is pretty cool. It's let's see. I don't have time, so I'm not going to do it. But it's you write ddt of the bk square, and you prove that that's 0 for anything that is not I, for k no I. And then since there is a conservation of the mass, the last one, the I1, has to be 1. So it's so the theorem that gives us the cascade is the following. So theorem, we call it sliding theorem. By the way, it will be great to have other constructions. I mean, this is the only one we know for the NLS that does something that makes it grow. So, just saying. Okay. So fix epsilon greater than 0 and n large. Then there exists, and unfortunately, x3 near in a neighborhood of epsilon of T3, neighborhood of T3, and x n minus 2, I believe, in a epsilon, this epsilon neighborhood. Okay, of T n 3 and 2 n minus 2, such that W, and also time, and a very large time, such that W, this map at times T of x3 is equal to x n minus 2. Now, the reason why this is not exactly x1, it is not exactly xn, just you have to give a little bit of room. It's not important, but still does the job. So basically, here you have your T3. You start close. This is my x3, and you move close to the T n minus 2 somewhere here. And that's the forward cascade. I want to give you just in the last 5 minutes the reason why do you believe?
You're moving the entire neighborhood of the torus and not just an
No, just a little bit. No, there exists. Basically, the way it works is you start here, and then you.
Small open set, not a
Yes, no, exactly. No, just saying that x3 exists in a neighborhood of that. In a neighborhood. No, it's not the whole neighbor. No. In fact, the way it works is you take this, you take a tiny little neighborhood, and you map. You stop in the first one, and if you intersect this, you just restrict, you go back, restrict this one, and you keep going, and okay. That's the idea.
You mean to find the...
To find the right one, yeah. It's a... exactly, it's a shooting method. Yes, Sally.
Before you erase that, so the system that you have, the main system, originally it was important is the defocusing. Is that information still recorded somewhere in the system?
Ah, right, that was defocusing. Yes, in this nonlinear part.
Sorry, what is the question?
The focusing, the fact that it's defocusing.
It's defocusing.
Yeah.
It's in the signs, right?
It's in the sign and in the energy. You see it also when you write the energy.
Using the energy? Or
No, the original energy.
For certain bounds, when you do this work at the end, the analysis you do.
But,
It's recorded in somehow those signs.
If the energy were coercive, this would give a worse additional strength.
Yes.
So it is important.
It is important the energy for the yes. It is important the energy that it keeps things under control. That's yeah.
So those signs they depend on
The sign here doesn't look like it, but when you do you write down what the energy is, it's very important that it's the right signs. That comes from the defocusing part.
You also need the conservation of momentum?
No, it's not used. It doesn't have a sign, so by this concerned. Okay, so briefly, before we close this part, why do you expect that you can do this? That's just like why do you expect that you can move from one torus to another torus, at least two of them? Just so there are some, so let's just assume that we have two tori, and it's two, let's say. And then I'm going to write, first let me write this solution, B1t, B2t. And this is e to the minus IT. This is not what we're going to use, but it's just to give you an idea why you expect that something like moving from one torus to another, it's possible. I'll tell you in a moment where omega is not very good. Let me call it alpha. It's a cube root of the unity. E minus 2 square root of 3t. And alpha is 2/3 t. Pi. No, sorry, pi. OK, so this is actually a solution of that system. Not with the particular initial data, just a solution. If you plug it in the equation, this actually satisfies the equation itself. And you see that when you take the limit as t goes to infinity of the modulo b1t and modulo b2t, what happens? Well, at t goes to plus infinity, when you take the modulo of this goes to 0, and this goes to 1, 0, 1. So when you tend to infinity, this tends to what I call the torus 2. The opposite, when you go to minus infinity of this, you go to 1, 0, which means T1. So this tells you that if you're willing to wait an infinite amount of time, you can move from the torus T1 from minus infinity to the torus T2 at plus infinity. So that gives you a sense how long the time is to go from one part to another. And this is only 2 of them. And then you have to make sure that when you keep going, you do not interfere with the ones already visited somehow. So it's much more complicated, but this is just to give you an idea of why you expect that you can move from one to another one. So I'm going to, since also, leave in 2 minutes. So this is just the analysis of the, so I'm going to pick up from here next time, the analysis of the dynamical system. And I already mentioned a little bit where the proof of the Hani-Posadeur and so on comes, which is collecting this behavior of the parameter n and just keep going with that. But the problem there is making sure that they are far away so that they don't interfere. Otherwise, they might cancel. And
to see why is this a good approximation also?
That's right. So, and I like what I said. So far, this is all we have. But it would be nice to have other kinds of subsystems that have the growth. So I'm going to pick up from here next on Thursday and just make the last few remarks. And then I have to decide what to tell you to finish it up. I wanted to go a little bit to the wave kinetic equation, just at least give you some results that we know in that sense. I will give you a little overview of that.
Thursday is your last one?
Thursday is my last.
Well, we can always extend it.
We can always extend it. Yes, I mean, if people are interested, I can talk more, you know. But anyway, this is for now. All right, so I will finish up next time. Thank you, guys.
Substance is the most natural way you can look at if you want to explain it.
I made a count for you. So.
Oh, good. Okay.
You want to go?
Going for lunch.
Sergio, are you going? Sergio, you want to go for lunch?
Yeah,
I have
let's
a
go.
guest who would come as well.
Yeah.
Ah.